I was a little bit mistaken in what I said earlier. I said, so you don't need to make any changes to the factor analysis. You can just run it with the default command. And then what you want to do is you want to use a package that you have to download for Stata called Fapara. And that one will run a parallel analysis for PCA and factor analysis. We have finished with factor analysis, and we are going to start with the basic tests. For some reason, we started with the most difficult, which is factor analysis. And now we're going to show how to do a t-test, which is very basic. And to do that, we need to get a different dataset. And I want to show you one that is built in Stata. It's called auto. And we can call it by using a command sysuse. And this is just to tell Stata that this dataset is stored in the system. This is 1978 automobile data. Very helpful. You'll often find it in examples in Stata. Concerns various variables from different cars. And if we want to do a simple independent t-test, we write t-test. And let's say we want to see if the price of a car is different from the two groups, foreign and domestic, car type, foreign or domestic. T-test price by foreign. This is the command to do a independent t-test. So the Stata knows that the first variable is the dependent, and that's the basic structure they use. The first thing will be the dependent. And then this is interesting because you actually have to specify the independent one in the options by foreign. And this is something you will find in several commands that you can use by as an option. And this essentially means, usually it means that you'll do something twice, first for the one group and then for the other group. But here it means that you're going to compare the price for the two groups. And we'll get this one out. And this might be a little bit, I mean, in the beginning, you always have to learn how to look at the various the outputs. If you're used to SPSS, for instance, this might be a little bit strange, but we see that we get the statistics for each group here. There are 52 domestic cars, 22 foreign. The mean price is, we see, are slightly higher for the foreign cars. Standard deviation is here, confidence interval is here. And then here we actually get, and this is maybe the biggest difference from in SPSS, you get 3 different tests, hypothesis tests, 3 different P values. So you may need to look at them to understand what they are. And essentially what it is that this and this is 2 one-tailed t-tests. So they only test if the difference is bigger than or smaller than 0. And you nearly always want to use a 2-tailed t-test, like statistically, unless you have a really good reason to hypothesize that the difference could only go in one direction. But there will be some times, but usually you're interested in the 2-tail, and that's what you'll find in the middle here. So the middle hypothesis is that the difference is different to 0. This is the sign for different when you're comparing something. Exclamation mark equals. And if you're unsure again, you can take a look at what it says here. And this is the probability that the absolute value of t is bigger than this value of t, which is the value from the table. If you're old-fashioned, you'll remember we had some tables we could look at to see if something is significant. Absolute value, if you're forgotten, is simple, and that's these 2 bars means the absolute value is simply the value without the sign. So it's not negative, it's always just positive, essentially. That's the non-mathematical explanation. So you'll essentially want to look at this middle one, normally. That's the t-tests. We will just move on from the t-test to the regression analysis. We'll keep using this dataset. Let's say we want to regress price on miles per gallon. Essentially, we want to see if we can predict the price of a car based on its mileage, or miles per gallon. And this is the output we get here. we have 74 observations. This is the F value. This is the P value of the model. Then we have the individual coefficients down here. This is the B value of the independent variable mileage, and this is the intercept. This is a significant effect, significant predictor. Mileage predicts price. This is the confidence interval. You may want the standardized regression coefficient, and we'll get that by specifying an option, and that option is beta. Now you'll see instead of the confidence interval, we get the beta value here. It is minus 0.47. So that's quite strong effect. We can actually, when we have done a regression, we can actually graph this if we wanted to. Like this. I'll never remember these commands for graphs because I don't do it often enough. So this I wrote it earlier, and now I was repeating it. This is making a graph, a two-way graph. This is a scatter plot, price and MPG, and then I'm fitting a line to that. And this will give us this. These dots are the scatter plots, and the line is the regression line, which is very helpful in visualization. We can do more things. Let's say that you don't want the confidence intervals to be 95 as up here, but you want them to be 99. Then we will just say that the level should be 99. And now we have the 99% confidence interval. Let's say we want to do a multiple regression. So instead of just using mileage to predict, we also want to use if it's a foreign or domestic car and the weight of the car, and we get this output. And now we just have the extra predictors down here. Now this becomes more interesting. This is the p-value of the model as a whole, and these are the individual p-values down here. It's a bit hard to compare the different coefficients, so then we will ask for the beta values, and we see that weight is heavily related to price. And it seems there might be a question in the chat. Feel free to use the mic as well if you want to, or type it out. Meanwhile, I will show you something else, and this is one of those selling points of Stata, at least at the department, and that is something called Reg Check. Okay, but here we have the question. Could we see the adjusted R2? And it is here. So we can actually already see it. Adjusted R square, it is right below the normal R square, normal R square. So you don't really have to do anything to get it. It's already there. I think you even actually get it. Yeah, you already have it when you have a simple regression. Like I said, Reg Check. This is a package, so you would need to install it. The way you install it is by typing sc install and then the name of the package. So you run this. I'm not going to run it because I already have installed it. It's always nice to use those help files when they're available. Reg Check says here that it examines regression assumptions. And then there are, let's see, 6 assumptions. It's actually made by Mehmet, a professor at this department. And this is a very nice one. And anyone who's used Stata will appreciate this one if they're doing regressions. This one can be run after a regression. So I'm going to run it now. It will test all the assumptions of the regression. Like it will test if there's a heteroscedasticity, if there's multicollinearity, and all those other difficult words. And it even color codes the output. So we can see here that we have a problem with heteroscedasticity because the Breuch-Pagan het test is significant. We don't have a problem with multicollinearity because the variance inflation factor is below 5. But we do have a problem with these 3 things and not with this. So this does tell us that we have some issues with our model that should be maybe taken into consideration. So Reg Check is very helpful to help you check the conditions, the assumptions of your model. And then there's another question, and I assume you mean the output from this regression analysis. And the question is, do these coefficients refer to standardized or unstandardized coefficients? So if you just run the, let's see, if you just run the regression model without specifying anything, the coefficients that you see in the first column will be the unstandardized regression coefficients. And that's more obvious now because they are quite high. So this would have been impossible if they were standardized. But this is maybe a little bit confusing because so now we are asking for the standardized ones, but they will not show up here. Instead, they show up all the way over here to the right. And you'll see they are marked by beta to tell you that this is the standardized coefficient. And it makes sense also because they are, as you can see, in between -1 and +1. So they will be over here. But we will always have the unstandardized on the left here. So we did the regression reg check, so we have problems. And this is the time to just mention something which is called post-estimation commands. And we have been using post-estimation commands several times. We used it a lot in the factor analysis, and we used it a bit now as well. But I didn't comment on it until then, and because I thought I needed to show you some examples first. So what is a post-estimation command? Well, you can start by asking, how did Stata know like where to get the numbers for this reg check? How did it know that this referred to this? And the reason for that is that when Stata does an analysis, it will temporarily store those the model, the output, in its memory. And if you then afterwards run specific commands, like typically a reg check or some of the graphs, then they will assume that you mean to use the data you just generated from a model, which is very helpful, because otherwise I would need to specify the whole model again after reg check, which I could do, but I mean it would take me maybe 10 seconds extra, especially as the models get more complex, then you appreciate not having to write anything extra. So reg check, what it does is that it's a post-estimation command, and it remembers that this is your model. So it's just going to put that model into this command and then run it again. And the same thing happened with this graph. Or at least I think so. I think, or maybe, I mean, I am writing in the variable, so it might be that this is not a post-estimation command. I didn't check it. What it means is that if I had just typed reg check without having entered a regression command first, then I would have gotten an error here because there is nothing to do the estimation on. And these post-estimation commands, you'll see them a lot, and if you're doing any structural equation modeling, there will be a lot of that there, and that's very helpful because in structural equation modeling, you'll be doing a lot of typing very long models. So that's especially helpful not to have to retype everything always. Another question is, how did I get the 95% confidence intervals? So let's just go back to the regression. I'll just copy it from up here. So if I don't type anything, then I will get the 95% confidence intervals by default. So they are the default setting. If I want to have, so notice, if I want to have the standardized regression coefficients, then I don't get the confidence intervals. So in Stata, you can't have your cake and eat it too. You can only do one of them. So if I can, for instance, let's try, I can say that I want 99% confidence interval and beta values, and I still only get the beta values. I don't get both. There is a trick here that I will, if we have time, we'll go through it. So there is actually a way to get both, but you have to trick Stata. Bootstrap command. I must admit I've never bootstrapped, but this seems like a good way to show off the help section. Help reg, and we see we get a help page for the regressions. Let's see if we can find something about bootstrapping down here. So immediately I don't see anything, so then I'm going to just cheat and search for it. Bootstrap. Here we have. Bootstrap are allowed. See a prefix. And we can also do VCE, which is the robust type of regression. So we can specify VCE and then bootstrap. Oh wait, they're actually not allowed in this prefix. So if you want to do any bootstrapping, I suggest you take a look at the help file and then just read these. And there's some links here. We can see maybe the prefix. And here we have bootstrapping. Yeah, and then if you read this, usually you'll be able to find the answer. More questions about regression? We can sometimes you'll want to center variables before you do regressions, and it's luckily very easy to center variables, and it's easy because we can use the power of the post estimation commands. So what I'm going to do, let's say that we want to center weight and miles per gallon. So we'll start by just summarizing them, weight and miles per gallon, but then I only want the mean. I'm just interested in the mean, and we need the mean to center. So we didn't get any output here, but Stata knows what the means are because we ran the command. And then I'm gonna generate a new variable which I called weight, and it's centered _c. And I set this variable to be weight equal to weight minus r mean. And this here means that Stata remembers it's the mean from earlier, the mean I just calculated. And we do the same with miles per gallon equals mpg minus r mean. And this has, now we have created two centered variables, and we can check that by just summarizing. So we'll summarizing weight and then weight C, and then we'll have mpg and mpg C, and we see here that, let's see, oh, this one didn't work. Did I have a, this one did not work. Probably I have a spelling mistake or something, which I could, yeah, I'll probably find it if I look at it. So let's just ignore this one. I made a mistake here, but I managed this one. So let's just focus on my successes and not my mistakes. And we see, let's just ignore this mistake, and here we have perfect, just what I wanted. So how do I know this worked? Because the mean of miles per gallon, the centered version, is 0, or essentially 0. If you have forgotten this mathematical notation, and I can just write it here. So it says here minus 4.03 e minus 08. That means essentially this, minus 4.03 times 10 raised to the 8th minus 8th power, which is essentially minus 0. And then there's a lot of O's here, or zeros, 403, and that is essentially 0. So this will always happen when you don't have, like you get approximately 0, but not necessarily exactly 0. And that's the point. Centering a variable means putting its mean to 0. So we did actually succeed in this. And then we can run the model with the, oh, sorry, I didn't show the command for that. So reg, and then price as usual, and then I enter the centered variables of miles per gallon and weight, and not of foreign, because foreign is a categorical variable that usually you don't want to center because that doesn't make any sense. So this will give you the the output, and you read it the same way as you would read it normally. But you just know that this is now the centered variables. Let's do a very short trip to interactions before we get to structural equation models. And now I need to use a different data set. So I'm going to go back into here, into my the main data file folder. And of course, then we have to use change directory, cd, to this. So we are now at my data folder. Here we have affairs, auto, and workout, and we are going to use workout. Use workout.dta, and we're going to clear out the rest of this. Now we have these variables. So what we want to do is make a moderation analysis or an interaction analysis where we see if workout hours is predicted by health and age. Health is, let's see, yeah, how important is health for workout? So it's an attitude. And age is, as you know, the time we have until we are dead. So this is the baseline regression, and we can run that first just to see. Looks like this. Age is significant, health is not. But let us try to make an interaction with health and age. So we make an interaction term between these two. Is your health attitude more important as you get older and so on? Or more important to cause you to work out? That's what we're predicting here. How many workout hours in a month? We see that the older you are, the less you work out. But your attitude has nothing to do with how much you work out. So to make a interaction, we start very simply again by specifying what the dependent variable is, which is workout hours. We then add the two predictors, and I'm going to prefix them with this C and C dot. And this is to tell Stata that these are continuous variables. And I have to do this sometimes, not always. But this will kind of tell Stata that we are dealing with interactions. And then I'm going to make the interaction term. And the interaction term, now you may remember that to make an interaction, we need to have those lower order predictors in the model. And then we add the product of those two terms, which is essentially health times age. And we symbolize that with the hashtag. This is C health, hashtag C age. And the C's are just there to tell Stata that these are continuous variables. We run this and we see here that we get the interaction term as its own line, and we see it is not significant. So here we do not have a significant interaction. And I'm just gonna do this again with, instead of health, let's take a look at workout hours, and then we are gonna do see age, but this time gender. So we're going to see if workout hours is predicted by age and gender. Gender is an indicator, meaning that it's dichotomous. You're either male or female. In this paradigm, we're not open for any other interpretation in this example. Then we create and that's why I have the I here, to make sure that Stata knows it is a categorical variable. And we make the interaction term like this. What did I do wrong here? I was a little bit too happy to add those dots. There, we see the interaction term is significant this time. So we have a significant interaction between age and gender. And how does that look? To figure that out, we can use a very helpful post-estimation command called margins. And what I'm going to do here is just write it out first. Yeah, like this. margins. Let's see if it works. First of all, it did work. Okay, let's take a look at it. This is the command. Margins, and then I specify some options at age intervals starting at 20 years and then increasing by 10 all the way up to 60, and for both male and females. Essentially what this does is it calculates the estimated values of workout hours based on these two variables. So first we have for the zeroth gender, which I think is male, I can't remember, when you're 20 years old, then for females when they're 20 years old, for 30-year-old males, 30-year-old females, 40-year-old males, and so on. This gives us a lot of essentially data points. And what I can use with these data points is I can put them into something called margins plot, which is another post-estimation command. This is to create a graph. I want a graph with no confidence intervals, no CI. Then the x-axis should be health. And then I'm going to make a line. No CX health recast line. Got an error there. And why did I? Oh, because of course I referred to something that doesn't exist. Health was wrong. I meant age, because we don't have any variables called health in our model. We have age. And we get this graph right here, which is very helpful because this graph symbolizes the interaction effect. This green one is women. This red one is men. So we see that there is not a strong relationship between, or not a strong relationship for age and workout hours for women, but for men, they work out much more when they're younger than when they're older. So the point here is that it's very easy to graph these interactions. Easy, of course, you have to not remember this, but you write it once and then you learn how to adapt it later. You can just copy it. That's what I did. I never remember this one, but I've copied it to a document and then I copy it back whenever I need it. So that was everything I wanted to say about that. And we are finally getting to the crescendo, which is structural equation modeling. So here we're going to have to use a different data set. We're going to use the one called workout 2. And we are here, I think we are in the data folder. We know that workout 2 is in this folder. So we can just use workout2.dta, clear, and we get it. And the question is, what if you drop no C in the margins plot? Well, now I've already gone past it, so I would have to go back. But I like your question because your question is, what happens if I try to change something? And my recommendation then is always just try it, see what happens. And sometimes you'll learn from it. Sometimes you'll get an error message, and then you know that, okay, this needs to be there. And if you didn't understand what the command or the element of the command did, then maybe you'll learn it now. And sometimes, for instance, in this case, my theory about what happens is that, because no C means no confidence interval. So I assume that if you drop no C, then you will get the confidence interval. But I recommend you try it. Maybe you can, and if you do try it, then tell us in the chat, so we know. But it's a very good thing to do, to just try things, and you'll often get error messages, and that's part of life. It's like, you know, getting up in the morning that's one long error message in its own right. So we're doing structural equation modeling. I guess I assume you know what it is. If you don't know what it is essentially a factor analysis put on top of a regression, or the opposite. So what it starts with is a confirmatory factor analysis. So this is similar to what we did earlier. We made a factor analysis. And these on the right here, you see a list of variables. And these are all attitudes towards something. It has to do with working out. And so there are a few assumptions here because I know the data set. So I will tell you those assumptions. Essentially, we want to make a structural equation model. And the command for that is sem, structural equation model. And we know we have one latent variable. Actually, yeah, we can write this here. Sem, one latent variable is called attractive. Attractive predicts the item's face and sexy. They appear here. How well does this following describe you as a person? You have an attractive face, you have a sexy something. That's one latent variable. Another latent variable is appearance. It is related to body, appear, and attract. And then I guess we can also do muscle. That one causes the items of muscle, strength, and endure. And then I guess we'll just do the last one as well. Weight causes L weight and calories, and C weight. So we have here 4 latent variables: attractive, appearance, muscle, weight, and weight. Notice that I've written the latent variables with a capital letter. This is a sign that Stata is case sensitive, meaning that a capital and a lowercase letter are not the same, they are different symbols. And when it comes to sem, for some reason, all latent variables are written with capital letters, and all items are written with lowercase letters. So I would get an error message if I wrote muscle with lowercase m. Each latent variable is also written within its own parenthesis with this arrow pointing to the items. And then we see here, we get a lot of output here. We can scroll down a bit, see that we have 187 participants. Then we see that we have something called a measurement model, and we have something called a structural model, which is, I guess, oh yeah, no, I didn't specify the structural model, of course. But this is how we get the measurement model of the structural equation model. And it's actually, I also really like to have standardized variables here. So I'll often specify the option standardized variables. So these variables we get down here, they are now standardized. This is the measurement model, which is also the CFA, or the confirmatory factor analysis. That was a question earlier, that how do we get the confirmatory factor analysis, and this is how we get it. The next part of doing a structural equation model is to do the regression part, which is to see how the different latent variables affect each other. And we can do that. I'm just going to get back our command here. And we do that simply by saying that, for instance, attractive affects appearance. So we just specify those hypothesized relations like this. Now this one seems to be impossible to get to. Oh, there. Okay, did not achieve convergence. This is a small data set, so I guess I have to. Well, here we get it. So this is a structural model, because that refers to the effects we see between the latent variables. So we can add more if we want to. But this is just to show you the commands, not to give you any more thorough introduction to structural equation modeling. But something that I think might be helpful, and now I'm gonna just copy some commands again. So we have our do file. Just gonna go down a bit. This block of commands here, or code here, is something that will create what's called a summary statistics data. which is something that I'm just mentioning because the first time I came across it, I was a bit confused. But it's often used in structural equation modeling, and the reason is that some analysis, or quite many actually, are based on just a covariance or a correlation matrix. And this, you see, this is a correlation matrix. It's just a matrix. We can't see the other side, but the other side is identical to this here. And so SEM is just based on this matrix. So the only thing it needs to calculate the structural equation model is the matrix. You don't really need all the numbers. And that's why it's sometimes helpful to just, instead of giving away your whole data set, you just give away the matrix, because then that's slightly more anonymous, because you don't have access to individual data points, because you don't need them. So you here you can make a summary statistics dataset. So I'm just going to start by clearing everything. So I've cleared my data set from here. Then I'm going to initialize the summary statistics dataset, and it has the variables x1 to x6. Then I say that there are 200 observations, and then I set the standard deviation for all those variables, all those 6 variables. And then here I create I list the correlation between all variables. I run that. And now we see we have these 6 variables here. And I think if we now browse, I think we'll see, yeah, you'll see this is just a correlation matrix. These are not individual data points. But I can make a structural equation model out of it. The first factor is predicted by x1 to x3. The second factor is predicts x4 to x5. And that will work. This is also a measurement model. And so now a question in chat is, where will we find the fitting indices? That's a very good question. Those are locked behind a post estimation command, which I have not written in the do file. And I might not be able to remember them, but I think they are something like estat goof. No. Or maybe all. No. I can't remember them. Help estat. Yeah, I should, I'll update them in the do file. It's some sort of post estimation command with goof and goodness of fit, and then you'll get them. So you run that after the structural equation model. Path and visual presentation of SEM, that's another good question. So annoyingly, the only way to get the visual presentation is to go, let's see, you have to actually, then you can't do it in the command window, you have to go in here, and I think, where is it? It's in one of these, maybe here, yeah. Statistics, SEM, model, building, and estimation. And you have to then actually kind of create it graphically here. It doesn't look very good, but this will also automatically create the commands you need. So my preference is to actually just do it all with commands, and then later I recreate the graphic in PowerPoint, because PowerPoint can create vector-based graphics. So it's a lossless format and it's easier for publication. But it is, of course, I mean, it's going to be work regardless. But there is unfortunately no way, unless they change it in the new version, there's no way to automatically create the graphic from your commands. The path coefficients, I assume that's what you asked about. That was what I tried to show earlier here. When I specify a relationship between, it's gone now. If I specify a relationship between, for instance, appearance and attractiveness, these 2 latent variables, then we'll get the path coefficients of the, or all the path coefficients are here in the column named coefficients. These are the coefficients for the latent variables, and these are the coefficients for latent variable on the individual items making up that latent variable. They are here in the coefficient column. The only reason I mentioned this, which might be confusing, is because you may, if you are working with examples in SEM, you might come across just this matrix. You're given this matrix instead of a data set. So I wanted you to know how to load it into Stata to work on it. I guess one further thing I could show you, and now we're essentially finished with all this crash course in Stata. I've shown you almost all the commands I want to show you. Only the last ones are just helpful things I have found on my own. So let's use sysuse auto clear. I've taken back the car dataset, and will you please run the multi-group command? I don't know how to run the multi-group command, so I'm afraid I can't do that. That's probably above. Or are you talking about, what's it called? Yeah, I might. That sounds familiar. Something I did maybe years ago. It's the yeah. Some brain cells are firing. I might have done that. Something to do with groups, but it's 1 or 2 years ago, and the knowledge has been deleted from my brain in order to make place for more Parks and Recreation TV series movie trivia. So I'm afraid I would need to go back and read to be able to do that. Yeah, but let's sometimes this data set has very nice labels, which are undervalued, especially when it comes to sharing data with others. So let's just look at how to change labels. And we can do that with the label command. So let's say that the variable price should have its label changed to, instead of the label being price, it should be the value of the car. And then we change it quite simply here. Very smart to do if you don't have, if the labels are empty. And if you don't like labels, you can do underscore strip underscore labels space underscore all. And then this will only remove value labels, not variable labels, apparently. So never mind that. You won't see the result here. If you, sometimes it's also very helpful to give value labels. So I think we'll see that if we use codebook. Yeah, so this variable here is coded as 0 and 1. And I believe that 1 is a 4, no, 1 is a, all right, don't we see it like this? No, I believe that the 0 is, yeah, of course. 0 is domestic and 1 is foreign. And you'll see I was a bit confused here because someone hasn't been good enough at explaining when they made dataset what the different values represent. So let's fix that. Usually there's a convention that you'll name a dichotomous variable after whatever is in the first position. So that's why I assume that there are 22 foreign cars and 52 domestic. But let's make sure that we make it even clearer, so I won't have to make that mistake again. So I'm going to define a label. Let's call it car label. And 0 is non-American. Let's do it properly. Non-American. That would be wrong. It would be actually American. So 0 is American, and 1 is not at all American. We have defined this label. Now we have to apply this label to these value labels here. So we say the values should change the label of the variable foreign, change it to the previously defined car label. And if we now take a look at foreign, now you see we get this value label we just defined. 52 American, 22 not at all American cars. So now it's easier for people like me to go back and see what was it actually that we got here. What do these values really mean? And of course, when you're the only one working on the data, you'll remember it. But often you'll be collaborating, and that's when this can be really helpful. And at least it'll save some time for them to have to try to guess at how you operationalize everything. You know, there's a ton of things that you could learn, ton of commands. I have over here, this is my cheat file. This is what I've been reading when we have been going through it. You'll see there's a lot of green here. All those green things are commands. And I'm gonna give you this file soon after I have made a few changes that I found some errors and stuff. So this will be on the OneDrive in maybe an hour or so, and then you can find it. And this will be everything that I did with some commands explaining why I did it, and so on. So this it's smart to just keep this when you're starting to get into Stata, to keep this as a kind of cheat sheet. So when you want to make a loop, for instance, you just copy my code and then you adapt it to however you whatever you need to do. There are only a few things left to say, and those are easier things. No more commands. We're done with the commands, apart from, of course, this little slide here. So I thought that what might be interesting for you is learning how to import or export data to Stata, because now, of course, I assume I have made you understand that Stata is the only way to work, and that SPSS should be abandoned immediately, and you should just use Stata until you're ready to use R or something. So previously, it was a bit hard to export data to Stata if you had it in SPSS. There is this package someone made called use SPSS. It doesn't work very well in 64-bit Windows, which is what everyone has these days if they have Windows. But there is a beta version, so it might work. Oh, this is outdated. It does work in 64-bit, but it's a beta version. But now there is you can export the file from SPSS. You can also import it from Stata in the new version. So those are two things I would try first. And you know, they have different algorithms, so it might be that one of them works better, either importing or exporting. If that doesn't work, then you can always go the long way through CSV, like I mentioned earlier. If that doesn't work, if that's hard, you can always just copy the data manually to Excel and then copy it into Stata. That feels to me a little bit too at risk of losing stuff, but it might work. There is an issue that I know of if you have really long variable names in SPSS. For instance, if you have data from Hunt, they have very long variable names, and they might be so long that they break when they get into Stata. There's a link here that will tell you how to deal with that. And this is also something I felt was necessary to say. If you get stuck, or rather when you get stuck, which will happen, what do you do? Like what I'm trying to say is you should not go automatically back to some other programs because you have some issues in the new one. You will inevitably get stuck somewhere and then have to learn how to get out of it. First thing to do is to get the help file for that function. I showed you that several times with the regression, and we tried to find that robust bootstrapping. Then we used the help file. It's, like I said, really good in Stata. I've been able to find most of my help through that function. So if you type help something, you'll get the help file. And if you're unsure of the function, if you only remember that you want to do regression, but you forgot what the command is, you can just type search regression, and it'll search for you and find what you need. Second best place to find help is Google. Just Google something. How do I do this in Stata? And you'll get a lot of very helpful help. If you have a very specific question that you can't find online, my third suggestion would be a place called Stack Overflow. There are many places where you can find information online, from Reddit, ResearchGate, Quora, and so on. Stack Overflow is the place I've found where they are the best at giving advice, the best at giving good advice. If I find that on the other places, there is a lot of bad advice being given and lots of people answering questions who maybe shouldn't be answering them. But on Stack Overflow, they have a very strict rule set. That also does mean that it's very hard to actually ask a question because people will downvote you if you haven't followed the rules explicitly. So you have to be very kind of attentive when you write questions there and make a minimal reproducible example. But I have been able to get a lot of help there from very smart people when I've been stuck, both in SPSS and R and other programs. And another thing I tried to show you, this is how to help your future self. You should make notes in your code. This is an example from something I did a year ago. This is not exactly clear what I did. Maybe I'll be able to get it if I look at the code long enough. But if I use this commands, then it's much easier. Now I see that what I do is I start by loading a dataset, a dataset of older men. And then I see I generate a variable that shows those who had a previous case of CVD based on whether they had either one of the following. And then I look at the frequency, respectively, in a sample of and so on. So this is invaluable. And I see so many people who don't write any good comments, and they invariably regret it later when they have to go back maybe for revision to the article, or they have to reuse the code and they can't remember what did the code do. So this, do use those commands for yourself. I mean, I've also sinned against this myself and not used good enough comments, and then I can't remember what I did. So I did definitely do this. And you may also want to, what I do, I always save code that I write, especially if it's not obvious how to do something. Then I'll save it. So you see I have actually so far 43 notes on how to do different things in Stata. And they've often been, and sometimes I have no use for it, but usually I do have. So you do it in a do file or a text document, whatever works for you, just save the command so you can use it for later. And you can use the do file I gave you as a starting point. This is essentially what we have learned. I think we did a lot in 3 hours. So this we should have gone through all of this: loading datasets, importing, exporting, transforming, handling missing data, creating variables, doing it under certain conditions, creating loops, if clauses, centering variables, creating some simple graphs, creating summary statistics data, or rather loading it. We didn't create it. We did lots of analysis. We downloaded files, packages from Stata, and we learned how to help ourselves. So the last thing, I think this is the very last thing I want to tell you is, and this is more like a tip on how to work with data. I would recommend that you try to avoid changing the original data as much as possible. So what I would recommend instead, so this is an example from the real world post GDPR. It is quite difficult to share data with someone else if you can't meet up. If you can meet up, you can give an USB with password protected content. But if not, you have to send it online, and that you have to find a proper way to do it and so on. So it can be quite difficult to share data with someone. So say that you and a colleague of yours in Berlin, you're working on the same data set, you're running analysis, and you, after doing lots of changes to the data, you find something very interesting and you want to share it to them. But for them to be able to reproduce the analysis, they have to do all the same things that you did in your data. And you didn't keep a good record. You have some memory of it, but you've just written down stuff like you have to center the variables, drop those, and so on. So they're spending a lot of time trying to recreate your data set on their own local version. Or alternatively, you have to send them your file, which can be difficult. So what you should do instead is you should just keep that base version of your file, both of you, and then you keep a long list, a long do file of everything you do, and you run that every time you start. And unless you are doing a lot of advanced stuff that will take a long time, it will usually run within seconds, and you'll get to where you are with dropping all missing variables, reversing variables, and so on. And then when you get to that point where you have found something and you want to share it with your coworker in Berlin, you can just send them the do file, which is usually contains much less incriminating things. And then they will be in seconds able to recreate the exact same data set that you have and be able to do the analysis that you did, especially since you probably also gave the commands for that specific analysis. So I would say this is a much better way to work. And I would recommend you to try to avoid hard coding as much as possible. Like when I did the loops, that was a way to save time, but also to avoid writing out things that I know will increase the likelihood I make mistakes, which I always do. And then I have to find the mistakes. And of course, lastly, practice makes perfect. It will take some time before you're at the same level that you are in the other programs you're currently using. But you will then quickly surpass that level when you get to use these slightly more powerful programs.